Hello! Thank you for taking the time to view my project. My study was the effect of surface cover on coastal dunes. Coastal dunes are sandy habitats stabilized by plants that separate the land and the sea. They act as buffers to prevent coastal flooding and excessive winds onshore. The ridge of dunes closest to the sea is called a foredune. It is the first layer of protection against storms. Foredunes absorb energy from storms, blocking waves and high winds from reaching further inland, and this causes the sand to be eroded from the face of the dunes. This erosion can leave the front face of the foredune scarped and reduced in overall volume, increasing their vulnerability to more change or erosion from future storms. Surface cover helps to stabilize dunes to withstand storms and reduce erosion. Foredune plants stop wind-blown sand, where it can then deposit at the base of the plant. Grasses such as Ammophila breviligulata are especially effective at capturing wind-blown sand and have been shown to reduce the aeolian sand flux of their environment. Dune fencing, which is installed in beach management efforts, mimics plant trapping the sand caught in the wind. Dune fencing can be fully or partially buried from sand deposited onto the dune, but foredune plants are adapted to this. These plants increase vigor when buried, growing upwards further, and develop a vast network of roots that help retain sand particles from erosion. American beachgrass, or Ammophila breviligulata, is a dune grass species native to North America. It has stiff, spike-shaped, pointy leaves that can reach up to 2 to 3 feet. American beachgrass spreads rapidly through underground runners called rhizomes, which are stimulated by sand burial to shoot upwards. Rhizomes allow the plant to share resources and better their chances of survival. The rhizomes are also close to the surface and easily damaged, hence why many beaches have rules against stepping on the dunes. Ammophila breviligulata was chosen because of its excellent erosion prevention properties and because it is the most commonly used dune building and stabilizing plant on the U.S. mid-Atlantic coast. The purpose of this study is to determine if different planting densities affect erosion and to find which density is the most efficient. The results of this study could help set a precedent on how to plant dune grass in the future to make dune grass plantings more efficient in retaining dune structure and therefore protecting areas further inland. It was hypothesized that compared to a condition of no plants, plants will reduce sandy soil wind erosion by providing surface cover, and erosion will decrease linearly with increasing plant density. The wind tunnel used for the trials is located in Waretown, New Jersey. It was built in 2016 as a research tool to explore coastal change. The diagram at the top shows the main parts of the wind tunnel: the funnel where air is sucked in, the sand bed, a space where boxes containing plants can be put, the fan, and the vent. The pictures on the bottom row show a side view of the entire tunnel, as well as a view of the funnel and of the fan from the inside. Boxes are lifted onto the platform in front of the tunnel using a forklift and then maneuvered into the tunnel with a pallet jack. Ammophila breviligulata was planted in a staggered configuration to prominent wind direction on June 16, 2020 in 1 meter by 1 meter test boxes. It was planted at 2 densities, mimicking the most commonly used spacings for planting efforts. 9 of the boxes were low density, with 18-inch spacing and 8 plants per box, and 9 boxes were high density, at 12-inch spacing and 14 plants per box. They were placed in the wind tunnel, and the bed was leveled using a 1-inch rake. The areas immediately surrounding the plants were leveled by hand. This shows an above view of the low density and high density, and then the null boxes, which had no plants. Once the boxes were in the wind tunnel and had been leveled, they were weighed using a pallet jack scale, and 5 pins were inserted to measure height, erosion, and accretion. The boxes were then subjected to a wind speed of 12 meters per second for 5 minutes, and then post-trial measurements were taken. And this diagram shows the location of the pins. And this shows the location of the pins in comparison to the locations of the plants. ANOVAs were run on the weight results, including high density versus low density versus null, and high density versus null. All of the results were significant when using an alpha of 0.01. The height results were also tested. None of these results were significant. The table on the right shows the average weight change by density, and the graph below shows low density versus high density kilograms of sand that were lost or gained. This graph shows low density versus high density versus null kilograms of sand lost or gained. And this graph shows millimeters of sand lost or gained, again by density. So, the results of this experiment showed that surface cover of Ammophila significantly reduced the amount of weight loss due to wind. Without any plants, the boxes lost an average of 7.125 kilograms. When Ammophila were added at a density of 18 inches, 7 plants per box, they gained an average of 1.7 kilograms. When they were added at a density of 12 inches, or 14 plants per box, the boxes lost an average of 0.667 kilograms. These results show that planting Ammophila at a lower density presents better results as there is a lower net loss. The weight results do not support the expected hypothesis. The Ammophila breviligulata plants help to trap more sandy soil, and the spike-shaped nature of the leaves allow the sand that was picked up by the wind to be deflected back to the ground. Higher densities of plants provide more opportunities to trap sand and therefore allow less sand to be eroded as well as less sand from the beach to be trapped in dunes. Therefore, higher density plantings would theoretically trap more sand and prevent erosion. It is hypothesized that the low-density boxes performed better because the high-density boxes created added turbulence in the wind tunnel, causing more sand to be displaced and therefore increasing erosion. The added plants in the wind tunnel may have caused irregular airflow. Eddies, a whirl of air formed from wind bouncing off of an object, would then circle back to the sandbed and disturb it further. This phenomena would be less likely to happen in nature because the air is not confined to a small space, and air can move in all directions, as opposed to in the wind tunnel, where it is confined to one. Further testing to determine whether low-density plantings would continue to form better in the field should be done to verify these results. And here you can see this is a high-density box inside the wind tunnel, so there's, of course, more turbulence in the air than there would be in a low density. Error in the methodology may account for some of the discrepancies observed as well. One possibility for error in the height results is the leveling of sand before in preparation for the trial. The sand in the areas immediately surrounded by the plants had to be leveled by hand. If one area was deeper or more shallow than another, it could affect the amount of erosion in that area. Another possibility for error was losing sand during the weighing process. The boxes had to be raised with a pallet jack to weigh them, and since sand was filled to the top, minimal amounts fell into the surrounding areas when the box was being lifted. Although precautions were taken to minimize this phenomenon as much as possible, it still accounts for a possible method of error. Finally, the contents of the sandy soil used provide a possibility for error. The sand used in this experiment was taken from Island Beach State Park in New Jersey and therefore contained bits of rock, shell, detritus, and other debris. Care was taken to remove larger debris. However, the results could still have been impacted if a piece was missed or if a smaller, heavier piece was in the sand. The results of this study are important because dunes are a vital part of coastal ecosystems. The outcome of this study can help inform what densities to plant dune grasses such as Ammophila at in order to minimize the amount of dune erosion. If this study were to be repeated, additional care would be taken to sift as much debris as possible from the sand before creating the bed. New methods for containing the sand while the boxes are being weighed should also be explored to minimize error in that respect. Additional research on how various densities of plantings perform in the field would also allow for these results to be verified. Possible follow-up studies could include exploring erosion levels when different dune plant species are used, or exploring erosion levels in a field site to see how the actual results compare to those created in a lab setting. To conclude, lower density boxes performed better at reducing erosion, and the results of the height differences were not significant. The addition of Ammophila breviligulata to the sand beds reduced erosion by weight significantly. Lower densities performed better than higher densities, although both were significantly better than the control of no plants. Possible sources of error that may have contributed to the height result being insignificant include leveling in the sand and small pieces of debris in the beds. In the future, further research to explore how actual field results compared to the data gathered in this study could help build on this knowledge and increase capabilities for preventing dune erosion.